Hello and welcome to this first example of deriving a second order system response in a control system. And in previous videos we have looked at some first order system responses, and before that we have derived some transfer functions and different types of inputs that we're going to use in this example. So if you haven't already watched those, it's worth going back and watching that full series of videos first. But we're going to jump in here with our first example, which is an RLC circuit. And again, in a previous video, we've already determined the transfer function of this particular circuit because we're taking the output as being the voltage across the capacitor here, VC. And we found the transfer function, which we call GS in the S domain. We found it to be 1 over SRC plus S squared LC plus 1. And so let's suppose that we have, or we're given a question, and the question is to calculate the response of this circuit in the time domain when exposed to a step input of 5 volts at time 0 seconds, given that the component values are as follows. We have R is 120 ohms, we have L is 36 millihenries, and we have C, the capacitance is 10 microfarads. Okay, so in our case, the step input of our circuit here, we're told it's a step input of 5 volts. This can simply be expressed in the S domain as 5 over S. Again, refer back to our previous video on different input types if you're not sure about that, but because it's at time 0, it's simply expressed as 5 over S. So we're saying VI, our input voltage, is 5 over S. In our previous videos as well, we also said that the output voltage, VO, is given by the transfer function multiplied by the input voltage, or the input expression in the S domain rather. So we know the transfer function, we've derived that in a previous video. We know the input in the S domain now, 5 over S. We're simply multiplying these together and we get something that looks like this. So at this stage, we could solve this system symbolically, and by that I mean just using these placeholder letters R, L, and C and all that kind of thing. The disadvantage of this is that the system response, and particularly the damping that the circuit's going to exhibit, depends on the values of the components. Different component values might also change the function or the response that we see here. Depending on the values, some terms might cancel or factorize or simplify. And it changes the result when we perform the inverse Laplace transform later. So what we're going to do is we're going to substitute those values in at the beginning here. Now that we have this function for our system response, our output, we're going to substitute the values in and simplify a little bit, but then perform the inverse Laplace transform with those values in place. And so with the values in, we end up with something that looks slightly messy. It looks a bit like this. We can simplify just using rational numbers, and I always advise using rational numbers in fractional form wherever possible in these examples. And so in this case, 120 multiplied by 10 times 10 to the minus 6 here, we can express that as 3 over 2,500 as a fraction. Similarly here, 36 times 10 to the minus 3 times 10 times 10 to the minus 6, we can express that as 9 over 25 million as a fraction. That keeps things a little bit tidier, and it's also going to help us later on as well. These fractions that we have here as well, if you're wondering where they come from, you can just use a scientific calculator if it gives results in fractional form, in the form of rational numbers here. I've not done anything special here, but when you work out those multiplications and get your answer in fractional form, you should get those results. Otherwise, the expression here for the output, the response, VO, is unchanged. I've just hopefully simplified a little bit. But one other thing we can do here is we can just tidy up a little bit we've got these s and s squared terms outside of the fractions in the denominator, so we can put them together and we end up with something that looks like this. We have 5 over s, and still on the denominator in brackets we have 3s over 2,500 plus 9s squared over 25 million plus 1, close brackets. And so at this stage, let's try to eliminate these complex fractions. We've used them in the first place to preserve some accuracy. What we don't want to do is start using decimals and rounding and all that kind of thing. We've kept precision here by using these fractions, but I also don't want the fractions making this formulation harder than it needs to be. So let's multiply all terms in the top and in the bracket on the bottom. Let's multiply all terms by 25 million. And so on the top now we have 5 times 25 million is 125 million. On the bottom now we have s brackets 30,000 s plus 9s squared plus 25 million. So first of all, let's not be too alarmed by these large numbers. If you've been following previous examples, we've never seen sort of numbers in the millions like this. On the bottom of the equation, we've got a quadratic expression in terms of s that we can factorize, and we're going to start to see that these numbers are going to get a little bit more manageable. In our case, that quadratic expression in the bracket here factorizes to this 3s plus 5,000 all squared, not forgetting the whole bracket was multiplied by s in the first place on the denominator there, so that's still there. Again, we're in the unfortunate situation where we have to rely on partial fractions, because when we come to refer to our table of Laplace transforms, what we have here doesn't really resemble any of the entries on the table. We're going to have to split this down into more manageable fractions, partial fractions, and hopefully that's going to help us perform the inverse Laplace transform. If you've been following our examples of first order system responses, we've already seen a couple of examples where we've used partial fractions. We're going to do it again in this example as well. So the idea being that we have VO equals this 125 million over S 3S plus 5,000 squared, and our intention is to split that into 3 smaller fractions, and the 3 fractions that we're going to split it into are going to have denominators like this: S 3S plus 5,000 and 3s plus 5,000 squared. And the reason for all those denominators is that they are all factors of that original denominator. We can take that original denominator and we can draw out a factor of s. We have a factor of 3s plus 5,000, or we could divide by 3s plus 5,000 squared. They're the 3 factors of that that original denominator there. And so we have now 3 new denominators made up of those 3 potential factors. The numerators of these fractions, we don't know what they are yet, and so we're just going to give these sort of placeholder terms A, B and C. We're going to work out the values of those next. So like in our previous examples, the first step is to multiply both sides by our original denominator here. And so our original denominator was S brackets 3s plus 5,000 squared. And we're going to multiply both sides by that. So the left-hand side here is now just going to be 125 million because we've multiplied and cancelled that denominator out. But each of the 3 terms on the right-hand side are now going to be multiplied by that same S brackets 3s plus 5,000 close brackets squared. And so we see something that looks like this. And again, like previous examples, that there'll always be some cancellation that can occur in each of those 3 fractions. So in the first one here, we can see the S terms are going to cancel top and bottom. On the second term, the B term, the 3s plus 5,000 is going to square with, is going to cancel with one of those 3s plus 5,000 terms that have been squared. We're basically going to lose the squared. And in the third term, we've got 3s plus 5,000 squared on top and bottom. They're going to both cancel one another out. And so we're left with something that looks like this. 125 million equals A brackets 3s plus 5,000 close brackets squared plus B times S times 3s plus 5,000 plus C times S. And we can find the values for A, B and C by substituting different values for S. And so I'm going to start by substituting S equals 0. So wherever there's an S in the equation, now it's 0. We have something that looks like this. And the reason I've done that is because automatically two of my terms, the B term and the C term, are now going to be 0 because we're multiplying by 0 in each case. And so now we're just left with the A term. Again, we've got a 0 in there. 3 times 0 is 0. So all we have is that 5,000 squared. So we have 125 million is equal to A times 5,000 squared. And just a rearrangement there, we find that A equals 5. Okay, next up, I'm going to substitute a guess of S equals minus 5,000 over 3. Why am I substituting minus 5,000 over 3 in for S? Well, the reason is to make those brackets, the 3s plus 5,000 terms, cancel to 0. So we'll see what we mean by this. Wherever there's an S now, it's now minus 5,000 over 3. We have something that looks like this. It's a bit nasty, but hopefully you can see that these brackets here, where we had 3s plus 5,000, well, I've now got 3 times minus 5,000 over 3. Well, 3 times something over 3, those 3's are going to cancel. So basically I have minus 5,000 plus 5,000. And so that bracket there is going to be 0. We'll end up with something looking like this, which cancels down to 0. And on 2 occasions, it happens again in another instance over here. Minus 5,000 plus 5,000 and ends up as 0. And we end up with just the C term because the A term has cancelled to 0 now. We're multiplying by 0. The B term is multiplied by 0, so that disappears. We're just left with the C term here. And so don't panic if the original formulation looks very nasty. You'll see here it very quickly cancels down. We have 125 million equals C multiplied by minus 5,000 over 3. And so we can do a little rearrangement here. We can say C equals 125 million divided by minus 5,000 over 3. I don't really like the nested fraction here, but either way we get a result here of minus 75,000. Okay, so now we know that A equals 5 and C equals minus 75,000. We can solve for B, and we can do this by substituting any number really for S, because we now know A and C. We can solve for B, but for simplicity's sake, let's use S equals 1. So every time we had S, it's now 1. So there was our original function here. Here it is with all of our S's with replaced with 1s. Notice that we've also substituted our values of A and C, which we know the values of both. A is 5, C is minus 75,000. So we've put those in there as well. And that immediately simplifies a little bit because we're just multiplying things by 1. Then we can simplify some more because we don't have S terms in these brackets anymore. So 3 plus 5,000 is 5,003. And so we have something that looks like this. And we can we can add 75,000 to both sides because we have minus 75,000 here. Adding 75,000 to both sides, we have something that now looks like this. And all I'm going to do here is I'm now going to subtract 5 times 5003 squared from both sides to get that b term by itself, and then divide both sides by 5003. And so b equals all of this as rearranged, but if we work it out, it comes out as minus 15. So by this point, we now know our values for a, b, and c. And so we can return to our original partial fractions, and they look like this. But we can populate them now. We have these values for a, b, and c that we've calculated. And what we can do is just tidy that up a little bit, because we're adding a negative in two instances here, adding a negative for that c term as well. Let's just write these as negatives. So we have something that looks like this: 5 over s minus 15 over 3s plus 5,000 minus 75,000 over 3s plus 5,000 all squared. And so now we've taken what was a fairly complicated fraction, or at least in terms of our Laplace transform table, it wasn't a fraction or expression that matched any of those in the table. We've broken that down into 3 simpler fractions, which hopefully do. There's a tiny little bit of work left to do before we apply the inverse transform though. Let's look at these 3 terms just very quickly. The first term here, 5 over s, hopefully if you've been following our videos, we recognize that is a constant, and we're going to be able to perform the inverse transform quite simply for that term. This term here, 15 over 3s plus 5,000, what I'm going to do is I'm going to take a factor out of that denominator on the bottom so that it more closely resembles some of the entries in our table. In fact, this second term here represents an exponential decay term, but in our table, it's in the s term has no coefficient. It's just s in the table rather than 3s. So what I want to do is I'm going to take out of that denominator there, I'm going to take a factor of 3 out. And I'm going to write it like this. Rather than 15 over 3s plus 5,000, I've now got 15 over 3 brackets s plus 5,000 over 3. So I've pulled a factor of 3 outside of both of those terms, and I've got that sort of sitting outside the bracket there. Similarly with this last term, I'm going to do something along the same lines. Minus 75,000 over 3s plus 5,000 squared. I want that s term sort of in isolation by itself without any coefficient. And so I'm going to pull this factor of 3 outside of the brackets, but notice that that 3 is squared because it's in this bracket that's been squared. So what I'm really pulling out is a factor of 3 squared. And so what we'll have is something that looks like this: 75,000 or minus 75,000 over 3 squared brackets s plus 5,000 over 3. And that bracket is all squared. Now that I've done that, I'm going to take these numerators and this sort of factor on the denominator. I'm going to pull these out of the fraction altogether, or form separate fractions as a constant outside of where we're going to perform the inverse Laplace transform. So what I mean by this is, rather than here in the second term, 15 over 3 s plus 5,000 over 3, I'm going to say instead that's minus 15 over 3 multiplied by 1 over s plus 5,000 over 3. So that 15 over 3, I've just pulled that as a sort of separate coefficient, because we're going to leave that, because it's a constant, 15 over 3, we're going to leave that as it is when we perform the inverse transform in a moment. Similarly, for this third term here, 75,000 over 9 is going to be outside of that original fraction there. So rather than minus 75,000 over 9 s plus 5,000 over 3 squared, we've now got 75,000 over 9, or minus 75,000 over 9, sorry, multiplied by 1 over s plus 5,000 over 3 squared. So I'm just taking those those sort of constant coefficients aside. They simplify a little bit. 15 over 3 is 5. 75,000 over 9 we could cancel down a little bit to 25,000 over 3, dividing the top and bottom by 3. And so we have something that looks like this. And now we can apply the inverse transform to these different terms. 5 over s we said was a constant, and so a constant, it's just going to be a constant of 5. Minus 5 multiplied by this 1 over s plus 5,000 over 3. Well, we said we're going to leave that 5 out of the inverse transform. It's still going to be in our result, but it doesn't, it's not affected by the transform itself. The transform, we're looking at this fraction 1 over s plus 5,000 over 3, and that corresponds with our exponential decay term. And so we see that our exponential decay term in the form of e to the minus at, well, a in our example is going to be 5,000 over 3. And so not forgetting our 5 that we've multiplied by, it's still here. So we have minus 5 e to the power minus 5,000 over 3 t. The third term here, which we have as 1 over s plus 5,000 over 3 squared, this corresponds with our entry here for 1 over s plus a all squared on the denominator. And that corresponds in the time domain with t e to the minus at. And so similarly, here, not forgetting to multiply by that factor of 25,000 over 3 that we sort of pulled outside, we're going to see something that looks like this. We have 25,000 over 3 t e to the power minus 5,000 over 3. A in our case is 5,000 over 3, sorry, for a. So we have minus 5,000 over 3 t as our power there. So this is our completed result here, which is correct, but we can factorize and simplify just a little bit. What we're going to do is we are going to pull out a factor of e to the power minus 5,000 over 3t, which occurs in a couple of terms, the second and the third term. We have that exponential. And so if we take that outside, we still have that 5 at the start, that first term. We're going to leave that alone. We have 5 now minus e to the power minus 5,000 over 3t multiplied by 5 plus 25,000 over 3t. Notice that both of these second and third terms were negative, but because we're pulling out a negative factor, that minus exponential there, minus e to the power, because that's our negative factor, it means that what's left behind now, they're both positive terms, 5 plus 5 and plus 25,000 over 3t. So that's hopefully just a little bit of a tidier formulation of the same result. But that's our output response in the time domain. VO is our output voltage in terms of time. If we wanted to plot this as a graph, say between 0 and 5 milliseconds, we would see something that looks like this. And this is our response in the time domain. We saw that it was a step voltage of 5 volts that was applied initially. So we have a 5 volt supply that's sort of switched on at time 0, but we see that the response of that circuit has this sort of S-shaped quality. We sort of have this curve upwards. We have this sort of transient and then leveling off, reaching a steady state by around that sort of time, 5 milliseconds. This is an example of a critically damped response. We talked about damping, circuit damping, especially the component values required for critical damping in RLC circuits. This is an example of a critically damped circuit, and we know this to be the case because when we review our previous requirement, thinking back to when we talked about damping in a previous video, we said that for critical damping in an RLC circuit, we need to observe this equation here, R squared equals 4L over C. So in our case, R was 120, if you remember right back to the start, 120 ohms. L was 36 millihenries, 36 times 10 to the minus 3. And C, the capacitance, was 10 microfarads, or 10 times 10 to the minus 6. And so when we put all that in the equation, we have something that looks like this. And if we work that out, we find that the the right-hand sides are equal. They both come to 14,400 in this case. And so we can see that the requirement for critical damping is met in this particular instance. And just as a recap, what we mean by critical damping is that the circuit reaches a steady state in the lowest possible time. So in our case, a supply voltage of 5 volts is applied, and the response of this circuit reflects the capacitor charging up to a voltage of 5 volts, reaching a steady state roughly around that 5 millisecond mark. And in the next section, we're going to look at a very similar example, but where this is not the case.